In this video, we're going to do some extra examples involving logarithmic functions. So remember, a logarithmic function with base a, where a is bigger than 0 and not equal to 1, is a function of the form log base a of x, and it's defined by the property that if y equals log base a of x, a to the y is equal to x. So a log function can be switched into an exponential function where the base of the log is the base of the exponential, and the other things switch sides. Okay, so if you were with the base, now you're not with the base. So let's do an example. So if I want to convert this to exponential form, so my base is 2, so it's going to be 2 to the x is equal to 6. Okay, so the base is the base, so the 2 is the base of the exponential, and then because the x was not with the base, it's now with the base. Now, to compute log base 3 of 1 over 27, we want to note that 1 over 27 is the same as 27 to the negative 1, and 27 is 3 cubed, so that's 3 cubed to the negative 1, which is 3 to the negative 3. So we want to know what power do I need to raise 3 to get 1 over 27. That power is negative 3. So this log is equal to negative 3. Okay, similarly, down here, we want to write 2 to the 6 as a power of the base 4. So what I'm going to do is say 2 to the 6 is 2 to the 2 times 3. So that's 2 to the 2 cubed. So that's 4 cubed. So this, so this log is the exponent I need to raise 4 to get 2 to the 6. So that's the 3 there. So that's going to be equal to 3. Okay, so the domain for a log function is always that the inside bit needs to be bigger than 0. And the range is the domain of a to the x, the exponential, which is always all real numbers. So if we want to do a transformation of a log graph, so this one they give us a hint because we haven't seen the log base 2 graph yet. So we're going to start with the graph y equals 2 to the x. Okay, so that graph, I'm going to have a point at 0, 1, a point at 1, 2, a point at 2, 4, and at 3, 8. And then at negative 1, 1/2. Okay, so that's where my points are, and then I have my horizontal asymptote at y equals 0. And the graph approaches that asymptote as x goes to minus infinity, and then grows infinitely as we go to positive infinity. Okay, so now we want the graph of y equals log base 2 of x. So this is the inverse graph. So what we want to do is switch all the coordinates x and y. So 0, 1 is now at 1, 0, and then I'm going to have a point at 2, 1, at 4, 2, and at 8, 3, and at 1/2 I'm going to be at negative 1. And my horizontal asymptote is now become a vertical asymptote. Okay, so my graph looks like something like that. Okay, so that's the graph of log base 2 of x. So all we did was switch the coordinates. So the x and y coordinates. So now I want to transform that graph. So the first thing I'm going to do is the x minus 4 on the inside. So this is y equals log base 2 of x minus 4. So what this does is shift 4 units to the right. Okay, so that includes the asymptote. So instead of being at x equals 0, it's going to be at x equals 4. And all the points you just add 4. So the old x goes to x plus 4. So I'm going to have, instead of at 1, 0, I'm going to be at 5, 0. 4.5 is where the -1 is. And then at 6, I'm going to be at 1. So if I add 4 to 4, I'm going to be at 8. So that's going to be there. If I add 4 to the 8, I'm going to be at 12. So that's 12 and 3. So the graph is going to look like something like that. So it's just been shifted 4 units to the right. So this is 12 and 3. This one's going to be 8 and 2. This is 6 and 1. This is 5 and 0. And then 4.5 and -1. Or how all those points go. And then finally, it is 2 or 3 times that. So it's going to be 3 log base 2 of x minus 4. So this is not going to move the vertical asymptote. Okay, but what it's going to do, so it's a vertical expansion by 3, sorry. So my old y value is going to be replaced with 3 times my old y value. Oops. Okay, so instead of being at 4.5 and -1, it's going to be at 4.5 and -3. Okay, the 0, 1 is going to stay the same. So if 0 times 3 is still 0. 6 is now going to be at 3. The 8, 1 is going to be at 6. And the 12, 1, that's 8, 10, 12, is going to be at 9. So that's up here. So you can see the graph has been stretched vertically, okay, by a factor of 3. So it's going to look something like that. So let's just label all these points again. So 4.5 and -3, 5 and 0, 6 and 3, 8 and 6, and 12 and 9. Okay, so that's what our graph looks like. Okay, so what's the domain and range of f of x? So that's our shifted graph. So the domain, so you can see from the graph, is going to be x bigger than 4, or from 4 to infinity in interval notation. So from the graph we can read that, or you could compute it by saying that you need the inside bit, so x minus 4, to be bigger than 0, which means that x has to be bigger than 4. Okay, now the range we can see from the graph is going to be the all real numbers. Those infinities are looking a little skewed here. So all real numbers. Now if we want to find the inverse, so I'm going to take the equation and switch x and y. So x is equal to 3 log base 2 of y minus 4. So I'm going to divide both sides by 3 so that the log is by itself. Okay, then I can do my switch. So it's going to be 2 to the power x over 3 is equal to y minus 4. So then if I add 4 to both sides, y is the exponential 2 to the x minus 3 plus 4. So that is our inverse graph. So f inverse of x here is 2 to the power x over 3 plus 4. Okay, and then the domain and range for the inverse. Okay, so the domain of f inverse of x equals the range of f of x, which we already computed to be negative infinity to infinity, so all real numbers. And you can see that from the equation now that we have it, because the exponentials have full domain, and then adding 4 is going to, there's nothing bad that can happen there. Okay, now the range of f inverse of x is equal to the domain of f of x, which we already saw was 4 to infinity. So y bigger than 4, which you can kind of see because this part approaches 0. So the smallest thing that you're going to always be a little bit bigger than 4. Okay, so this thing, maybe I could write that here. So without using that, 2 to the x over 3 is always bigger than 0. So that means 2 to the x over 3 plus 4 is going to be bigger than, 4. I add 4 to both sides. Right, so you do plus 4 plus 4. So that means that your inverse is always going to be bigger than 4. Okay, so now let's try some solving equations. So let's say we want to solve this equation. So right now I have it, a log is equal to some number. So the first thing I'm going to do is do the switch. So that's base 5 to the power 2 should be equal to x squared plus x minus 5. So that's 25 is equal to that. So I'm going to subtract 25 on both sides. So that's going to give me a 0 on the left. And then I have x squared plus x minus 30. So now I want to factor this. So I want two numbers that multiply to give negative 30, add to give positive 1. So that's going to be a positive 6 and negative 5. So this is going to factor as x plus 6 times x minus 5. And then, so that equals to 0 when one of the factors is 0. So I get x plus 6 is 0, or x minus 5 is 0, which means that x is negative 6, or x equals 5. Okay, now we want to check those answers. So if I plug in negative 6, okay, I'm going to have log base 5, negative 6, so that's going to be 36 plus negative 6 minus 5. So that's log base 5 of 36 minus 11 is 25, and that is equal to 2 because 25 is 5 squared. Okay, so that one is a solution. Now if I plug in x equals 5, I have log base 5 of 25 plus 5 minus 5. So that's also log base 5 of 25, which is also 2. So that one works as well. So here we have two solutions. So we could write our solution set is the set containing negative 6 and positive 5. Okay, let's try this one down here. So here I have a single exponential. Okay, so I want to first solve for the exponential. So I'm going to get rid of that 4. So move the 4 to the other side. So that's going to give me e to the x plus 1 is equal to 5 over 4. Now I want to do the switch. Okay, so when I'm going from exponentials to logs, this is going to be log base e, okay, of 5 over 4 is equal to x plus 1. Now log base e, that's just ln. Okay, so this bit here is actually ln of 5 over 4. I just wanted to emphasize that the base was e. So this is using switch to logs. using the relationship. Okay, now if I solve for x, it's going to be ln of 5 over 4 minus 1. And if you compute that, it's approximately negative 0.7769. Okay, so that would be our answer. And we don't need to check it because it's an exponential function, so it has full domain, so there's nothing to really worry about there. Okay, so now the applications. So in chemistry, we have the pH scale. So you probably are familiar with this. It measures the acidity versus the alkalinity of the water. So that's whether it's acidic, or basic. And it uses the formula pH is negative log of H plus, where H plus is the hydrogen iron concentration of the solution, okay, in moles per liter. So less than 7, we say the solution is acidic. Greater than 7, we say they're basic. And if they're exactly 7, then like pure water is, then it's neutral. Okay, so neither acidic nor basic. So these things increase by factors of 10, so that's why they use a log scale. So let's just go to the question here. So suppose you test apple juice and you find the hydrogen ion concentration, so the H plus value is 0.0003. So this is measured in moles per liter. Okay, so then using the formula, the pH should be negative log, so this is log base 10 of 0.0003, so the H plus value. And if you compute this, you get approximately 3.5229. Okay, so the pH that we get is less than 7. Okay, so we would conclude that this solution, this apple juice, is acidic. Okay, if we test the hydrogen ion concentration of ammonia, then we get an H plus value of 1.3 times 10 to the negative 9. Okay, that's scientific notation. So what that means, let's just write that here. So you take your, so I'm going to have to add a bunch of zeros. Okay, so you take your decimal, which was there, and the negative 9, you want to move it 9 times. What is going on there? So you want to move it 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's where it would go. So that's what that number represents. Okay, so that means that the pH is negative log of that number. So it has 8 zeros and then a 1, 3. Okay, if you were to compute that using your calculator, you get approximately 8.886. Okay, so here the pH is bigger than 7, which means that the solution is basic. Okay, so or alkaline. One more. So another thing that's measured that increases in intensity by factors of 10 is the earthquake, the Richter scale. So it also uses log. Here's the formula. So the Richter scale number, the Richter rating, is computed by doing log of your intensity divided by this threshold intensity. Okay, so this is a movement that can be barely detected. Okay, and the intensity I is given in terms of multiples of the threshold. Okay, so suppose you have your seismograph set up at home and there's a vent and you measure that the intensity was 989 times the threshold intensity. So then the Richter rating would be the log of the intensity I, so 989 times the threshold over the threshold. Okay, so that's actually log of just 989. And if you compute that, you get approximately 2.995. So that would be the Richter rating for that event. So those are using logs in some different scenarios. So that's sort of the basics for logarithms.